Understanding triggering is one of the most important things when learning how to use an oscilloscope. This is even more true on today's digital storage scopes. At its most basic, an oscilloscope monitors voltage over time for each channel or signal that is connected to it. But in its normal mode, it doesn't just continuously show the most recent voltages. To help the engineer visualize the signal, a scope overlays waveforms from different points in time that share a specific characteristic that is of interest to the engineer. This characteristic is the trigger event. There are several important settings to discuss before we discuss the variety of trigger methods. First, trigger hold-off is a setting used with many of our trigger types. This sets the minimum time between two triggers. This is used to make sure the instrument doesn't trigger on an unwanted signal between the trigger events we want to capture. Here we are looking at a series of pulses. We can use the trigger hold-off to make certain we only trigger on the first pulse. Now, the trigger event is the first pulse in each pulse train, since the pulses end before the trigger hold-off expires. Each time the pulse train starts again, a new waveform is posted to the display, overlaid with the previous signals. This is how we use triggering to show how a signal changes over time. This makes it easy to see how many pulses are occurring in a set. Another important concept to understand in triggering is pre-trigger and post-trigger data. Typically, the scope places the trigger point in the center of the display. Points to the left of the trigger occurred before the trigger. This is the pre-trigger data. Points to the right are the post-trigger data, as they came after the trigger event. During a real measurement, as the trigger moves around, you can see how much of the data is before or after by referring to the infographic at the top of the display. The orange trigger marker denotes where the trigger occurs in the waveform. The grayed out area denotes how much of the data is off the display. This is especially important when using the deep memory of the oscilloscope. Once you stop capturing waveforms, you can then move to view parts of the waveform that are originally off the screen. Triggering is a reference point for how we compare and evaluate signals. Understanding the basic concepts and different methods of triggering makes signal analysis more effective.
Horizontal system and controls. The horizontal controls include a position knob to adjust the horizontal position of your signal. This can be used to best position the area of interest for the signal you have acquired. For example, if you are mostly concerned about events leading up to the trigger, you can use the position knob to move the trigger to the far right of the display. The scale knob adjusts the sweep speed of the scope. Turning the scale knob counterclockwise will slow the sweep time down for slow signals, and turning it clockwise will speed up the sweep time for faster signals. Adjusting these two controls will allow you to optimize the scope and display to show the detail needed to properly analyze signals of interest. The horizontal menu button is used to enable delayed sweep, as well as 3 different sweep modes. They include XT, XY, and roll. Let's look at some signals to illustrate these capabilities. Here we have a pulse with some ringing. We can use the scale knob to optimize the sweep time, and then the position knob to see areas of interest. We can effectively zoom in on a signal by selecting delayed sweep. Delayed sweep can be selected using the horizontal menu button. Another way of selecting it is to push the scale knob. With delayed sweep enabled, you will now notice 2 versions of the signal. The top half of the display shows the signal as first acquired, but now there is a narrow section framed by blue blocks. This narrow section of signal is what's shown in the lower trace after being expanded to fill the display. You can now use the position control to look at areas of interest. Three time-based modes are available in the horizontal menu. The most commonly used one is YT, or voltage over time. This is the mode we've been using up to this point. The second choice is XY. In XY mode, you can have one signal drive the x-axis and another signal drive the y-axis. Using this mode, you can analyze phase relationships between signals. So we'll go ahead and push menu, and we'll change our time base to XY. And now you can see a phase relationship between channel 1 and channel 2. The third time-based choice is roll mode. Roll mode does not wait for a trigger or for memory to be filled before the signal is displayed. The signal will roll from right to left of the display. This can be very effective for finding very slow asynchronous events. Here we have a pulse that's difficult to show in YT mode. Since it's so slow and doesn't happen very often. Switching to roll mode, we can now easily see the event. As you become more familiar with the horizontal system and controls, you'll be able to more effectively acquire and analyze your designs and prototypes.
Vertical systems and controls are some of the more basic controls and channel controls that allow us the ability to better view a captured signal and move the signal around on the screen. To go over some of the different vertical systems and controls that we have available with this particular scope and our scopes in general, I'm going to first turn on channel 1, which is connected to a 1 kilohertz sine wave, and then I'm just going to go through the menu over here and then go over some of the other sort of knobs associated with it. So to start out with, for channel 1, along with all the other channels, we can choose how it's being coupled, either with DC, AC, or ground. And these can all be associated independently of each other. We can also turn on or off a bandwidth limit. For this particular instrument, we're limited to 20 megahertz. We can also change the probe attenuation we have going on. And then we can also choose if we want the signal inverted or not inverted. And then we can also go ahead and select coarse or fine sort of position adjustments, which I'll go over a little bit later. And then we can select our different voltage readings we want to do with, either with watts, amps, or volts. Some of the other things are we've got a position knob over here which lets us move the signal up and down on the display. So this is a way that you can move around different other signals. Say we had channel 2 turned on and we wanted them to be separate from each other. I can move channel 2 off of channel 1 like this. I can also quickly recenter channel 2 by just pressing the knob, and it's going to quickly recenter. Another aspect are we can just change the position with the scale of the particular signal by rotating this knob, and we can make it larger or smaller, and then we can also choose between coarse and fine sort of measurements, which are displayed here. So right now we're in fine, so I can make smaller sort of scale options, and I have to rotate a lot more to get a scale change. Or I can go with coarse sort of options, which are more the presets, which will let us snap in between much larger scale sort of positions. The vertical systems and controls are pretty universal for all of our different oscilloscopes that we have, but they allow you to move around the signal and view the signal as you need.
Screen capture to USB stick or Ultra Sigma. Printing a screenshot of your signal is important for archiving and documentation and can easily be done using a USB stick or Ultra Sigma software. Here we have a simple square wave using the probe compensation output on the scope. We can save an image to a USB stick formatted FAT32 with a push of a button. First, we'll insert the memory stick, and the scope will detect it and display USB device detected. Now we will push the print button This is the green button with a printer icon on it. Once pushed, the scope will automatically create a default file name and transfer a PNG file over to the USB stick. Two other options are available that will allow you to save screenshots to a PC using a USB or a LAN connection. The first option uses Regal's Ultra Sigma software. Here we have Ultra Sigma software up and running, and we'll make a connection using a USB cable between your scope and a PC. Once connected, the scope will be listed and identified by model and serial number. We can now right-click on the instrument and select Operation to Print Screen. The third option is to use Ultrascope software. Ultrascope brings up the display and a user interface for remote control from your PC to the scope. With the display showing your signal of interest, you can then right-click while over the display and select Print Instrument Screen and then save the file. Both Ultra Sigma and Ultrascope can be freely downloaded from our website. Using these two methods, you'll easily be able to save and document your scope acquisitions.
I will be covering our basic probe set and different items that are shipped along with our passive probes. To begin with, the probe kit comes with the probe, which for this model has an attenuation switch to switch between 1 times and 10 times. There's a compensation screw to adjust the probe's compensation. There's an alligator ground clip used to ensure a safe common ground. Next, there is the probe hook or witch hat, which is used to connect the probe to the circuit. Then there is the adjustment tool, which is used to change the probe's compensation. The marker rings are used to color code the probe with the scope. The grounding spring is used to improve the high frequency response of the probe itself. And finally, the insulating cap used to prevent short circuiting when probing with just the tip of the probe. To demonstrate kind of how to basically do some probing around with the probe itself, start off with, I'm going to connect our probe by pushing on the slot in the scope itself. There's 2 pins on here, so you have to line it up before rotating on. So once you push it in, you then rotate it, and the probe is then attached. After that, I've got a grounding hook and the probe tip. So I'm going to attach the grounding hook to the ground on my proto board here, and then the hook tip to the sine wave. And as you can see on the scope, we're actually capturing a sine wave. So that's basically how to probe around with this probe itself. Also, as a side note, the compensation screw is located right here on this probe. And then on the back side is where you'll find the attenuation switch. So you can switch between 1x and 10x. Next, I'm actually going to disconnect the probe hook but leave the ground on. And I'm going to take it off and push on the insulating cap. So this is actually covering the ground on the probe itself, and now with this tip is where I'm actually capturing the signal. So I'm going to capture the same sine wave with just the cap itself. As a side note, this sort of metal ring here and the metal ring here are both ground, so the insulating cap is just covering this so you don't short against this to the tip. Next, I'm actually going to take the alligator clip off and then put on the grounding spring. So this is used more to capture your high frequency sort of signals, and basically signals where you're having potentially some weird high frequency response. And then with this you can use it to, the outer spring is the connected to the ground and your tip is still the hot end of your circuit. And you can use this to capture your signals like so, and you can just probe around for more of your high frequency sort of areas. So that's some of the basics of our probes itself and how to use them and what they can be used for different probing techniques. Probe compensation is necessary for calibrating a new or used probe for a particular oscilloscope. It can help improve signal quality being viewed by the oscilloscope. In order to demonstrate how to properly compensate your probe, I've connected a PVP2150 passive probe to a 1 kHz square wave that's being produced by our scope. And then with the screwdriver that was sent with the probe set, I'm going to change the capacitor in the probe, the passive probe, to change the compensation. So right now the probe is overcompensated. I can undercompensate it along with properly compensate the probe. Once it's set here, you generally just need to leave it alone, but it's an important aspect for dialing in a new probe or a new instrument for a particular probe to get a properly read signal.